So, okay, welcome everybody to this online format. It's a pleasure to have Sandeep Sahany give the first talk at the ICTS Monsoon series. Well after the monsoon, but that's okay. And just to say a couple of words, I guess some of you, at least I see names here that were present at ICTS Monsoon Day some time ago. And some of us, including, by the way, I'm Amit Apte. I'm a faculty at ICTS, just in case there are people who don't know me. And some of us, including Rama, Govindrajan, and Vishal Vasan, and Srikar Vadlamani from TFR CAM, have been thinking about various types of monsoon models and starting to think of understanding the mathematical aspects of monsoon in a way. And in this effort, of course, we would like to understand about the monsoon itself in a much more detailed way. So this seminar series will be an attempt to try to interact more with people from the atmospheric oceanic earth sciences community. So the first speaker is Sandeep Sahany. As I said, he's no stranger to Bangalore. He did his PhD at CAOS with Ravi Nanjundhaya and Venugopal, and then moved to actually after that he moved to UCLA, or yeah, I think yeah. So in UCLA, and from there he moved to Singapore Center for Climate Research as a research scientist, and then joined IIT Delhi, the Center for Atmospheric Sciences, and currently he's at Center for Climate Research again. I guess maybe on a sabbatical. I'm actually not very sure. So today he will talk about numerical modeling aspects of the monsoon. Over to you, Sandeep.
Thanks, Amit. Good afternoon, everyone, and thanks, Professor Rama, for inviting me to present or share a few things that I have been doing, or we have been doing at IIT Delhi for this ICTS Monsoon Seminar Series. I'll be talking about some numerical modeling aspects of the Indian summer monsoon. This will be a brief outline of my talk. I'll just give some background, not much. I mean, there are way better people in the audience who know about monsoon more than me, so I'll not spend more time there. And then I'll just talk about model biases in ISIM, that's the Indian summer monsoon simulations. Some recent improvements, and I'll summarize after that. So what I'll not be talking about is changes in Indian summer monsoon, global warming, and things like that. And then teleconnections and ISVs, seasonal forecasting, predictability. These are all, I mean, elaborate discussions in themselves. So I'll not get into all that. So what are the important drivers of monsoon? So it's basically, it is taken from Turner et al. 2011, but this has been people have been working on it since ages. So, but then Turner et al. Has summarized it, so I'm just quoting this one paper. So it's the SSTs. When I say the SST, the sea surface temperatures, both near and far, it's both over the Indian Ocean and the Pacific and the Atlantic. The snow, such as the ocean snow cover, and then the local soil moisture atmosphere interactions, and the orography. Orography, in the sense it's mostly the West African, the East African orography, and then the Himalayas and Tibetan orography. So all these govern the overall large-scale monsoons, and then there are intricacies in the individual components of monsoons. So this was the Indian summer monsoon rainfall 2020, taken from the IMD website. So on the left, we see the 1st of June to 30 September rainfall. That's actual rainfall. The middle panel is the normal rainfall, or the climatological rainfall. And on the far right, we have the anomalies. So we had a good monsoon this year. The actual looks very similar to the normal, but in terms of anomalies, yeah, I mean, we have overestimates, we have positive anomalies and also the negative anomalies over regions. So yeah, this is just the rainfall, but there are many things that happen to cause this spatial pattern. This is just the end result. This figure comes from Turner and Anomaly 2012. So in the top, we see 200 HPA winds plus trim rainfall, that's the shading. And the bottom, we see 850 HPA winds plus the SSTs, and also it shows the orography, the Himalayan orography in the African mountains and so on. So when we talk about monsoon, there is a large seasonal change which is seen in many variables, whether it's winds, whether it's precipitation, whether it is the temperature gradients, the pressure gradients, the OLR, and so on. So there are signatures in all kinds of variables. So say, for example, we can see the low-level jet here, which we don't see in the winter. So the left is summer, right is winter. So the low-level jet. And then also what we see is wherever we have this high SST, if you see here, we have this higher rainfall both in the summer and winter months. So this large scale, so it's a large scale phenomena. Basically, it's a combination. It's mostly driven by the ITCZ, but then there are local things that change some of the interactions. Yeah. So this is what it looks like overall, and then we want to be able to model it. So when we start modeling monsoons, we don't do anything very different than what we anyways do in a global model. I mean, we have the equations of the conservation of mass, momentum, and energy, and then we have the large-scale dynamics, and then the grid scale is taken care of by the equations themselves, and which are resolved, and then there is a subgrid scale, which we parameterize, so that's the physical parameterizations, which take care of the subgrid scale. And on a very simplistic note, there is an initial state, and then we compute the tendencies, and then those tendencies multiplied by a time step size gives us the delta changes. This delta changes added to the initial state gives us the future state. And then the model keeps marching, and then we have a simulation out of it. So that is what it is in a basic sense. So as far as resolved scale is concerned, things are more or less fine in models. Of course, there are problems there as well, but not as big as the subgrid scale or the unresolved scale, which we call as the physical parameterizations. So convection parameterization, for example, is one of the most important in terms of governing the precipitation biases that we see in models. So this is the figure taken from Menon et al. 2018, just to show that how the monsoon progresses. So these are basically isochrones. So for every grid point, we can actually compute based on rainfall when exactly there is the onset of the monsoon. And then if we join the grid points which have the onset on the same date, we get these isochrones. And then so we can see that there is this southeast to northwest movement along the trough. So that is basically the monsoon onset. So for example, here we see 1st June, it arrives in Kerala, and that is what IMD says as the monsoon onset over India. So this is the onset process, and then there is a withdrawal process as well. So in terms of components of Indian summer monsoon, so there is an onset of monsoons, there is withdrawal of monsoons, and many things that happen in between onset and withdrawal in terms of intra-seasonal variations. And all of these are modulated by teleconnections through the large-scale teleconnections, say, for example, the SSTs over the Pacific or Atlantic, for example. So next is the existing model biases. What are the model biases that we have in present-day models? I'll just divide them into spatial pattern biases, that's the mean biases, onset biases, withdrawal biases, biases in the precipitation partitioning, that's the convective and large scale partitioning, and biases in precipitation distribution. So I'm not covering few things here like the ISVs and teleconnections here, but and also the low pressure systems here, which are very important for the precipitation biases that we see over India. So this is a figure from Sperber et al. 2013. So what it shows here is we have, so this is CMIP 5, that's a couple model intercomparison project phase 5, multi-model mean minus GPCP, and this is CMIP 3, multi-model mean minus GPCP. So GPCP is the observations. Of course, there are observational uncertainties as well. So I mean, if someone wants to do it in a better way, you can actually take an ensemble of observations to remove observational uncertainties, but the larger message will not change much. So if you look at CMIP 3 multi-model mean, so we see this wet bias over the Arabian Sea, and then Himalayan mountains, and then the foothills, and then the northern and western equatorial Indian Ocean here, and this large dry bias over central India. So, and this is also there in CMIP 5. We still have this wet bias over the western equatorial Indian Ocean and Arabian Sea, and dry bias over the central India. If we look at CFS V1, the IITM model, there also we have the dry bias over India as reported in some of the papers. Even in the IITM ESM version 1, also the dry bias was there. Of course, things may be improving, but overall the dry bias is still there. And we at the DST Center of Excellence in Climate Modeling, we have been working with the NCAR, CESM, the Community Earth System Model, and then the atmospheric component of it, that's the Community Atmosphere Model, as the base model for improvements. So we also see the wet bias over high topography in the Arabian Sea and the Western Equatorial Indian Ocean, and dry biases over the central India.
Excuse me.
Yeah.
Can you please define the bias in a simple sense, maybe?
In a simple sense, yeah. So it is basically, in a very simple way, it's the difference between model and observations. So it's just the seasonal mean. Say for every grid point, we have a seasonal mean produced by the model, and we have a seasonal mean that we see in observations. If we do a model minus observations, a very simplistic measure, and then we get the difference. That difference I'm calling as bias.
Okay.
Yeah, so if it is positive, I say white bias. If it is negative, I call it as a dry bias, because we are looking at rainfall.
And actually, I was also going to ask, is this shown as percentage, or what are the units here? The 4
These are in millimeters per day.
Okay.
Yeah.
And so what are the values I should associate with the actual values?
In terms of percentage, I will show in the next slide.
Oh, okay, fine.
Yeah, so you can actually see the values which you can associate with these biases. So this is, so here we saw the multi-model mean. That's the mean of bunch of, say 30, 40, 50 models. Here we are looking at individual models, and we are just looking over Indian land, and we are comparing with IMD observations. So this is the IMD observations, June to September rainfall. This is in millimeters per day. And then these are individual model biases. Each of these panels are individual models, and the biases of these models. This color bar here shows the biases. If you see a blue, it is a wet bias. If you see a red or a brown, these colors, brownish colors, you have a dry bias. So what we see is most of the models will have this dry bias over central India with different magnitudes. Almost all the models, excepting very few, I would say. Say, for example, this GFDL model has almost zero bias. And then there are models like, say, MIROC 5, which is a Japanese model, which in fact has a positive bias. It's probably the only model which shows a positive bias. So one way of improving our models is looking at them and so what exactly they have. I mean, I'm not saying that the positive bias is good. What I'm saying is there is something which is actually causing more precipitation there. So what is it that is causing more precipitation there? And then there is a nice example here. So there is MEROC 5 here, which is, and then MEROC ESM, that's the Earth System model. So when you add a biogeochemistry component to a couple model, you get an Earth System model out of it. So this is an Earth System model, and then most of the physics should be the same. So what is it they have done that the Earth System model is showing a dry bias over central India, and then the couple model is showing a wet bias over central India. So these kinds of things, I mean, when we start looking at individual models, maybe there is something which we can learn. So, yeah. So, continuing with the spatial pattern biases, this is a model. This is taken from one of our students who actually had his PhD viva a couple of hours ago. So Raju Pathak. So this is from his paper. This is the model genealogy. So what it means is, although we have, say, 50 odd models in CMIP, so CMIP is a couple model intercomparison project, which is used by IPCC for the assessment reports and so on. So although we may have 50 odd models, they actually have branched out and then from some base models. They are not developed from scratch per se. So they are basically relatives of each other, more or less, with some differences. So if you look at model genealogy, I mean, there is a clustering method which is used by developed by Retorknutti from ETH and so on. So we have used that, and so if we divide, so we have these 4 groups, 4 clusters of models. So for example, here we see the Hadley Center model. So this is a UK Met Office model. So there are 2 versions. One is the couple model with the carbon cycle, and then without the carbon cycle, I guess. So this there's the Earth System model, and then there is this Axis model, which is the Australia and CSIRO, CSIRO model. So they have the same atmospheric component and then different ocean components. So the algorithm picks them and then finds them that they belong to the same family. So similarly, say GFDL models, this NASA GIS models. So the algorithm finds out that, okay, and then we can again go back and check whether they are really the same or not by looking at, say, what parameterizations they use and so on. So there are 4 clusters basically. We can divide them broadly. The models can be divided into 4 clusters. This is observations, and these are the 4 clusters. There's a mean patterns for the individual clusters. You see 1, you see 2, 3, 4. And then this is biases of the, so I'm just looking at the convective component of the biases. And this is also the convective component, actually. So if we look at the biases, we see those positive biases over the Western Equatorial Indian Ocean and Arabian Sea, and then Burmese Mountains and Bay of Bengal here, and then dry bias over India, and then of various magnitudes, depending on which cluster you are in. And then interestingly, there is one cluster, GC4, which actually has very little, I mean, so the wet bias is much reduced both over the Western Equatorial Indian Ocean and over central India. So there is also something to learn from this category of models. What is it they're doing different, which is causing this? So, and then the hatching that you see is basically what it means is, so we have compared both. So there are 2 things. One is the IMIP and then CMIP. CMIP is couple models. IMIP is where we have prescribed SSTs run in an IMIP mode. So if we take the IMIP model biases and compare with the CMIP model biases, and if the IMIP bias is, say, around 75% or more of the CMIP model biases, we say that because in IMIP the SSTs are prescribed, you have the perfect SSTs, only the atmospheric component and plus the land component can induce some biases. We say that most of the biases are coming from the atmosphere because the ocean is perfect, you have perfect SSTs. So we see a lot of hatching, which says that over large parts of the region, the bias is coming from the atmospheric component. And then we have looked at what in the atmospheric component, and then we found that the convection scheme plays a major role, and there are 2 specific processes. One is the closure in the convection scheme, and one is a trigger in the convection scheme, which actually is important to to govern these biases, which basically decides, I mean, the models being in different categories. And then, so this is the precipitation partitioning. So let us forget about this panel, top panel here, and let us just focus on the bottom panel here. What this shows is these blue lines or these blue bars are convective precipitation biases. These red ones are large-scale precipitation biases. And then this line here is the total precipitation bias. So we see that largely models have negative bias in their large-scale precipitation, and many of the models show positive bias in their convective scale precipitation. So why is this important, and this partitioning? Because the convective and because one might argue that, okay, why do we bother? I mean, we just want to know what is the total precipitation, but the difference between the large scale, because both of them have different latent heating profiles in the atmosphere, and because of that, the circulation changes and so on. So based on what is your latent heating profile. So if we don't get this partitioning right, many things go wrong. So there are cascading effects.
Excuse me.
Yeah.
In the previous plot, can you just go back? Yeah. So these 4 clusters end up explaining how much variance in the data. Typically.
How much variance in the data?
Like you mentioned, I think this is some sort of a clustering method that was used.
Yeah. So it's basically a pairwise clustering is done of say we have 50 models. We do a pairwise clustering of all of these.
Okay.
Say 1, 2, 2, 3, 3, 4, and then and then keep reducing the clusters, and finally we get 4 clusters.
Correct.
Yeah.
So I think you must have achieved some sort of, based on some WSS plot or something like that, some sort of.
Yeah, but then so I got your point, but then we have not looked at how much variance exactly these explain.
I see. Okay.
Yeah. All right, so this was about precipitation partitioning, and then so even if we look at CFS, so this is TRIM, it's the satellite estimated precipitation on the left, and then we have CFS V1, CFS V2. So and then there are a few papers here. So from IITM, so what they say is 40 to 50% convective precipitation should in principle be there, but both of the models show around 80 to 90% convective precipitation. So which is a large overestimation, which is the general thing which we saw earlier. And then we move on to onset biases.
Sorry, can you go back 2 slides?
2 slides?
Yeah, here. Can you just briefly say the difference between large scale and convective precipitation? And
so in observations, for example, say we have a big cumulonimbus cloud with a large anvil. So the rainfall, the low intensity rainfall that you get from the anvil, so that may be treated as large scale precipitation, which happens over a large area. And the high intensity rainfall that you get from the cumulonimbus over a smaller region, that may be treated as a convective scale precipitation, basically. But in models, it is done by 2 different parameterization schemes. The convective precipitation is produced by the deep convection parameterization scheme. The large-scale precipitation is produced by the convective precipitation. I mean, convective is mostly produced by deep convection, but there is also shallow convection parameterization. But then large-scale precipitation is produced by the cloud microphysics and macrophysics parameterization scheme. So in the model world, things are slightly different. Yeah. Does that answer your question?
Yeah, sure. Yes.
So I talked about this, and then onset biases. Overall, there is a delayed onset in most CMIP5 models. So this is GPCP, and this shows the pentad. That is the, say January 1st to 5 is the first pentad, and then 6 to 10 is the second pentad, and then you have around 50 something pentads in a year. So if you look at the pentad in which onset occurs, this is GPCP's observation. This is CMIP5 multi-model mean, so there is a delayed onset in the models, in the CMIP5 class of models. And so in CFS V1, V2, it's by a week. There is a delay in a week. Say, for example, it should happen in January 1st, June 1st, it happens a week later, so June 7th, 8th, something like that. and then delayed onset by a couple of weeks in SP-CFSV2. This is another version of CFSV2, which was super parameterized. So it uses a super parameterization, convection parameterization. And then in the model that we are using, it has actually an early onset by a week or so. There is an early onset. The end of May, last week of May, it shows an onset. And withdrawal, there is overall delayed withdrawal. If you just, without getting into the details, if you just look at this GPCP and then compare the multi-model mean, there is an overall delayed withdrawal. So we have a delayed onset, delayed withdrawal of monsoons in the summer monsoon. And then if you look at the distribution of precipitation, which is a very important thing. So this is just over Indian land. What we see here is, so this black line is IMD observations. And then if you look at individual models and look at the daily distribution, so most of them have this issue of there is a frequent drizzle is there, or rather not most, but many models have this drizzle problem. They overestimate the frequency of light precipitation. And then most of them don't get the extremes correctly. So if you see here, all of these models kind of, they're not able to get these extremes here that you see in observations, excepting there is one model, MIROC, which is a Japanese model, MIROC 4H, which is a high resolution model also, and then it's able to get these extremes. But then, yeah, most of the models don't. This is a paper from, this is a figure from Untitled 2014, CFSV2. What they show is for various regions, how the model does in terms of distributions compared to observations. So we can see that most of the regions, Central India, Arabian Sea, Bay of Bengal, all there are problems everywhere. And then Equatorial Indian Ocean, it does reasonably well. So what are the reasons? These are a few of the reasons. Uncertainty in empirically designed parameter values that are used in the physical parameterization schemes, as I mentioned earlier. Inadequate representation of coastlines and topography due to coarser resolution of models. Lack of scale awareness in parameterizations. So say, for example, when we go from a coarse model to a fine model, we expect that just by increasing the resolution, our simulations would improve. That doesn't happen. It happens to some extent because the coastlines and topography and land use, land cover, for example, are better represented, as the lower boundary conditions are better represented in the model. So simulations improve, definitely. But our parameterizations are not scale aware, so they're not flexible enough to know the relationship between large scale and subgrid scale. So they use the same relationship between the large scale and subgrid scale. So we don't see as much improvement as there is potential for. And then there is inadequate representation of convective subgrid scale variability. Say, for example, many of the things, some of the parameters are very deterministic. So those all issues are there. And then etc. So there are other problems as well. And then I'll move on to recent improvements. So while there are biases and there have been improvements, and people have been working on it. So it's not as if there is no improvements. So I would like to share this figure. This figure I recently got from this website called Carbon Brief, and it's a not-for-profit, and then they do a lot of journalism and things like that, and then other things on climate change, etc. So on their website, they have this article about climate models. How do climate models work? 2018 January. So, and they say who does climate modeling around the world, and then for India they have nothing. I mean, so the general perception is probably that there is no climate modeling being done in India. But yeah, there is a perception, but things will change because this for the first time we have participated in CMIP 6. So definitely perceptions will change, and then we will have a blue dot here very soon. So next. Improvement in CFS V2 versus V1. So yeah, I mean, I'm just showing that the dry bias still persists. Doesn't mean that there have no improvements. There have been improvements in various other things, which I'm not going in details here because of time constraints. I'll just show some of the things that we have been doing at the DXC Center of Excellence at Climate Modeling with our students and other research staff. So I'll just share formulation and implementation of a spatio-temporal dependent convective relaxation timescale in CAM5. So this is the convection scheme. So what it does is for closure, it assumes that, so closure is a problem in the sense that when we talk about the consumption of instability by the large-scale instability by the convective processes, that's a stabilization of the atmosphere. It's difficult to close the system of equations. So at what rate does it consume instability? So what should be the cloud-based mass flux basically? So people come up with various assumptions. So this is one of the ways of closing it is, okay, the cloud-based mass flux is consumed at a rate which is directly proportional to the amount of instability. That's Kp. That's the vertical integral of buoyancy basically. And then there is the convective time scale at which it consumes instability. And then in the default model, this was a fixed value of 3600 seconds. So what we did is we wanted to eliminate this thing. So what we did is we removed this, and then we introduced a dynamic formulation where the convective time scale actually depends on the depth of the cloud and the updraft vertical velocity. And for the updraft vertical velocity, we have used something which I had done earlier while at UCLA. So using this, I will not get into the details of the equation. So earlier in the default model, this entire thing was a constant value of 3600. It doesn't change in time and space. So after introduction of this convective relaxation time scale, which is dynamic, and this is an animation of that, so you can see all this. It acquires different values over different times and different grid locations. So what is the impact of all this? So if we look at the impact, so on the top we have this is the total precipitation from observations, and then we have the convective component, large scale component, and then second row we have the default biases. That's the default model biases, total convective large scale. Third row we have the new, that's we call it d tau, that's the dynamic tau. Tau is the convective time scale. So again, total convective large scale. And then this is d tau minus default CAM5. So we can see that overall, say for example, it reduces this Western equatorial Indian Ocean bias to some extent, as we can see here. And if you do d tau minus default, we get blue colors, so it is reducing, but not reducing enough to be able to remove this dry bias. So, and then of course over the Himalayan foothills also it is reducing the bias, but not reducing enough. So yeah, there is some improvement, but there is still further way to go. And then I will show what it does to the annual cycle of precipitation in terms of onset, withdrawal, and then precipitation distribution. So this is the default model, as I shown earlier. It showed an early onset. So the onset has corrected quite a lot. It is much closer to observations. And then withdrawal also, withdrawal was also corrected to some extent, if we see here. So, there is another figure which is more clear, and I'll show that. But then it actually spoils the distribution of precipitation. So we see that the default model was underestimating the moderate and heavy rainfall events. But then the changes that we did, it actually made it even worse. So yeah, you get something improving and something else going wrong somewhere else. So this is something called as the meridional tropospheric temperature gradient, which is basically a vertically averaged it's a mean of tropospheric temperatures and the difference between two boxes. So whenever this crosses 0, we have the onset, and then again when it crosses 0 towards the negative side, we have the withdrawal. So we can see that, so this line is the onset, and this line is the withdrawal. This is error interim, which is reanalysis, proxy for observations. And this was the default model. And then what we did with that, the onset has improved. And then the withdrawal has also improved. So there has been a significant improvement in the overall length of the rainy season. So if we get into details, so we have seen how it comes from changes in the cloud distributions and radiative fluxes and all that. So I'll not get into the details of that. There is another thing that we did, which is one was the convective adjustment time scale. So that improved few things, accepting the precipitation distribution. And of course, there are still biases in the precipitation pattern, like the dry biases. So what we did here is, and also one might ask why these two. So one of the reasons of these variables, these are also known to be sensitive parameters, meaning you change these parameters slightly and then you get a lot of change in the end result. So these are parameters, and then there are many parameters used in these parameterization schemes. Not all of them are sensitive. So one of the easy way to correct models is find out the sensitive parameters and work on them. So these were two of the sensitive parameters, and then also they are important for various reasons. This is the data, and then we also looked at the entrainment formulation in the model. So entrainment is just the mixing of cloud air with the environment air. It's a non-cloudy air. So in the default, so as a plume grows, it keeps entraining from the sides and the top. So it mixes with the environment basically, and then this entrainment actually affects the buoyancy of the parcel. So it affects to what height a cloud will grow, for example. So, and then in the current version of the model, it has a default fixed deterministic space-time independent value of 1 × 10⁻³ per meter. So it's like if a parcel of 1 kg rises by 1 kilometer, it will mix with another 1 kg of air in this 1 kilometer that it goes up. So that is what is the formulation right now, very simplistic formulation. So what we did in the model is, there were a few things done by some other researchers elsewhere in different contexts. So there is this entrainment, so we wanted to have a stochastic mixing. So this epsilon d, and then this is Poisson distribution, and then it's multiplied by this. So this is basically model difference, the difference between the two heights basically where the parcel goes. There's epsilon d is 0.2. This is taken from one of the papers, Roms and Kwan. So they came up with these values from larger dissimulations basically. So because these are unobservable, so we don't observe them. So we use LES for estimating them. And then L0 was prescribed as 100 meters. So, and then we have this, and so we have this stochastic mixing. And then if we do that, and then we look at what happens to the biases, again, this similar kind of figure. So this is the total precipitation, observations, convective, then large scale. Second row is for default, third row is for stochastic Cam5, and then fourth row is for stochastic minus default. So here what we see, one of the major improvements is there has been significant reduction in this Western Equatorial Indian Ocean. But still, this has reduced slightly, as we see here. If we do stochastic Cam5 minus default Cam5, we are getting positive values here, which means the dry bias is reducing, and negative values here, which means the wet bias is reducing here. So that is progress in the right direction. But still, some biases are there. It's not completely gone. So we still have to work hard to get rid of this. And most of these biases, improvements are coming because of the convective component. And most of the improvements over the central India is coming from increase in the large scale component. So what happens to the distribution? So interestingly, here the distributions are, I mean, the problem that we had earlier, we are able to solve this. So we have very good distribution, especially of the medium and extreme precipitation rates for a model of, the spatial resolution of this model is 1 by 1 degree, which is still coarse to get these extreme precipitation rates. But still, we get this extreme precipitation rates, which means the model is doing quite well in terms of distribution. And then if we look at the same metric for onset and withdrawal, so onset, here we see that not much change in onset. Although in the data we saw improvement in onset, here we don't see much improvement in onset. But withdrawal, yeah, so withdrawal is good here as well. So withdrawal has consistently improved, but the onset improved in one and not in the other, and then distribution improved in one, not in the other. So next I will talk about some cloud parameterization sensitivity that we have done recently, which just got published. Got published online a couple of days ago. So what we did here is we perturbed 17 parameters from the cloud microphysics and macrophysics parameterization scheme. And then we did a sensitivity analysis using a package, which is a software package which perturbs the parameters and looks at the sensitivity. So we conducted 180 simulations for 6 years each. So it's around 1100 years of simulations, 1 by 1 degree model. So, and on the x-axis, we have the most, we have the most sensitive parameters. On the y-axis, we have the various components of ISM. Here we have on the first and then top row, we have the onset. Here we have the withdrawal. Here we have the low-level jet, or the Somali jet strength. We have the tropical easterly jet, which is at 200 hectopascals. Then there's a Hartley circulation strength. And the MTTG, that's the meridional tropospheric temperature gradient that I was showing. And this is another thing called as eastern shear of zonal. The zonal wind shear, basically. So equatorial, yeah, something. Zonal wind shear. And the shear, that's the difference between the low levels and the high level winds. So what we see is for different parameters, we see different sensitivities. So for example, we want to fix, we want to delay the onset. So this is in the y-axis, if you move up, you are delaying the onset. So say for example, there is this variable RH-min L, which is the minimum relative humidity threshold for low stratiform clouds used in the cloud parameterization scheme. So if we just want to delay the onset, you just keep increasing this, and then you will keep delaying your onset. So when I say this, I'm not saying that if you do this, other things will remain the way they are. It's possible that something else may get worse somewhere. So a more balanced approach to model improvement is required. But so this at least we know that, okay, this parameter, there is something here which can actually delay your onset. And similarly withdrawal, there is something here which can actually delay your withdrawal. So there's another parameter also which can actually delay your withdrawal. So similarly for other variables, we have other things. So say for example, the meridional tropospheric temperature gradient. So it's not as if it just happens blindly. There is a physical mechanism behind why it happens. So this MTTG, which controls the onset and withdrawal, for example. So this has similar sensitivity if you look at this withdrawal, for example. So there are physical mechanisms how it happens. But then if we want to deal with a particular process, a particular component of the monsoon, there is these kinds of parameter sensitivities help. So this final, there is this model performance metric which I'm showing here, which what it does is that so it takes precipitation and surface air temperature over India, and then it computes an overall metric. So closer you are to zero, better your model is. This is CMIP 5 model. There were 41. we are using 41 models, and SMIP 6 models, we are using 33, but we have around 50 odd models. We are yet to look at all of them. So one information is this multi-model mean. So closer you are to 0, the westward propagation of this line is good, is progress. So there is progress. So SMIP 6 models in general overall are better than SMIP 5 models, but then yeah, so there is still a long way to go. And then CSM2, for example, is one of the better performing models which we are using as a base model, both in SMIP 5 as well as SMIP 6. So with this, I'll summarize. Of course, I have not talked about teleconnections. I have not talked about intraseasonal variations, and talked about, for example, the impacts of, say, for example, how NGO simulation affect. So there are various other things we have looked at. I'll not, for the brevity, I'll not show other things. But to summarize, I would say that biases remain even in simulating the mean spatial pattern of Indian summer monsoon. Example, dry bias over Indian land, Eastern Bay of Bengal near Burmese mountains, wet bias over Western Equatorial Indian Ocean and Arabian Sea, and aspects such as onset, withdrawal, intra-seasonal variations, both the COSY biweekly mode as well as the ISOs, the 30 to 90 day oscillations. And then the COSY biweekly mode is not that bad, but the ISOs are, there are problems both in what we have done and also from what I understand from the IITM publications. There are a lot of problems in ISVs. And then, of course, teleconnections. And then not to mention, these get further complicated by, say, cloud aerosol interactions, land use, land cover, both the actual land use, land cover, and changes in time and climate change. So it is a moving target in some sense, but yeah, we are also trying to catch up. And when we say we, I mean, when I say we, it's the entire model development community, better observations, better supercomputers, and then there are more concerted efforts to do that. So in terms of way forward, we need, I think, I mean, this is my opinion, I think we need to form process evaluation groups to at least at a country scale. And then, of course, we can have international experts as well. So this is something which is done in the Met Office, for example. The UK Met Office has process evaluation groups. So there are groups of people looking at a specific process. So that that simplifies and speeds up the model development cycle, for example. So process, I'm not sure whether IITM already has one, but yeah, so this is a good thing to have process evaluation groups, focus on specific processes, identify the most sensitive processes which have the most impact, and then try to constrain those processes. One of the examples is process-oriented diagnostics, where we have a diagnostic, and then we link it to what is it in the model which affects this diagnostic, and then we go back and then try to correct that component of the model. So it's something called process-oriented diagnostics. There is a full volume of special issue on process-oriented diagnostics recently, I guess, maybe a year or so ago. And then look at error growth analysis. So what I mean by error growth analysis is the systematic biases which we see in models, say, after running it for, say, 10, 15, 20, 50 years. So that can, I mean, a large part of it is, it can be seen in the initial phases. So say, I mean, even if you run a model in the NWP mode, so say, I mean, say we start the model with a warm start with, say, use error 5 or error entering, which is the reanalysis, and start the model with these conditions. Initially, I mean, say in 5 to 10 days, we will start seeing the errors, the systematic biases. So, and then we can see how these errors are growing, and then go back and look at what is it in the model that is causing these errors. So this is something worth exploring. And then, of course, as Isaac Hell says, the gap between simulation and understanding. So many times we are able to simulate things without understanding them. And then also there are many times where we understand things, but we are not able to represent them. So there is a gap between simulation and understanding, which needs to be bridged using simple models, theoretical models, and then, say, models like QTCM and then other models, which are very simplified models, basically, or So yeah, and then we need scale-aware parameterization, which I raised earlier as well. We have, say for example, if we look at the first assessment report of IPCC, which happened in 1990, and the sixth assessment report, AR6, which will be coming out in say April, May next year. In this 30 years, the model resolutions have changed from say somewhere around 500 kilometer grid sizes to around 100 kilometer grid sizes, a 5-fold increase in resolution. But still, not much work has been done in terms of scale-aware parameterization. A large part of improvements that we see is coming from the better representation of coastlines and orography and land use, land cover. Yeah. And then, of course, we can use LES, large area simulations, to constrain some of the processes like entrainment, for example, which are unobservable. So we can use this to understand processes better. So say, for example, David Roms has done quite a lot of work on this, and then Chris Brotherton has done a lot of work on this, and so on. So we can learn what they are doing. So yeah, I mean, people are also using machine learning, for example, to improve parameterizations. Mike Pritchard at UC Irvine, and then Chris Brotherton is also using it. Paul O'Gorman at MIT is using it, and then I think there is also some work going on at IITM that started looking at how to use machine learning to improve parameterizations. So overall, with all these improvements, a more holistic approach is required in simulating the monsoon drivers, and then the causal pathways by which they affect the monsoon, so that there is a faster improvement in monsoon simulation while we try to catch up with the changing nature of monsoons with climate change, for example. With this, I'll stop, and thank you very much for listening. Thanks for your attention.
Okay, thanks a lot, Sandeep. Yeah, if anybody has questions, the easiest thing, I guess, would be to unmute yourself and then ask the question.
Can I ask one?
Please, yeah, go ahead.
Hi, Sandeep. This is Rama.
Hi. Yeah.
I have two questions for you.
Yes.
One is like, in the, you clustered these models into families, like 4 families.
Yeah.
In that, like you showed that one of those families was doing probably better on the Indian dry bias than the other 3.
Yeah.
But if you look at those models individually within a family,
yeah,
do they all do the same thing? Like, earlier you'd shown another figure with some 1 or 2 models which had a wet bias, not a dry bias.
yeah, true.
So do those also belong to these families, and do they get clustered together?
So I mean, to the extent that we have seen, so you're probably talking. So just one minute, I'll just point my laser pointer here. So this biases you're talking about.
No, I was talking about the previous slide from this, where you
okay.
that one.
So
you showed these ones with wet bias. Where do they belong in the clusters?
Yeah,
do they
so
belong together?
Yeah, this is a good question. So they definitely belong together in the cluster. If you see, here is my rock. So this is, but then the MyRock 4H and MyRock 5, which are doing well. So here they are. So the both 4H and 4.5 and 5 are here. But then the ESM, which was not doing, I mean, which had the dry bias. So they show in 2 different families. So there is something fundamentally different in the atmospheric components, I think. So yeah, so they are in 2 different families basically.
Okay.
Yeah. And then as far as the question whether all the models in a group behave similar, yes, they behave. They may not be exactly same, yeah, but they're more or less similar. Yeah.
Okay. So my next question is like, you were talking about, we need to improve parameterizations by LES and machine learning. I mean, are these like 2 alternative ways you think we should proceed, or like will one aid the other, LES and machine learning?
So in my opinion, we use both of them. There is a synergy between them because we can, whatever LES we use as proxy for very high resolution observations, which we don't have. And then the way things happen in an LES, say there is either we directly implement that in our parameterizations, or we make the machine or the neural network, say for example, learn how things happen in using the LES data, and then just use it in the parameterization. In fact, we can just say, for example, this can this network can take over the parameterization, for example. So there are synergistic ways of doing things. That is how I see it. Yeah.
Okay, thanks.
Yeah.
Amit, can I ask a question, Debashish?
Yes, please. I just go ahead and ask questions whenever you want. Too
Sandeep,
much
that's
difficult to monitor who is asking and who. Yeah, so go ahead, please. Of course, Devashish.
Sandeep, thank you.
Hello, sir. How are you?
All right, all right.
Yeah.
Heroic calculations you're a student and you have done.
Thank you.
I wanted to ask about this last sentence you have on your slide.
Yeah.
A holistic approach in monsoon, simulating monsoon drivers. Maybe you could spend a minute and tell us what you mean.
Yeah, so what I mean by this is, say, when I say monsoon drivers, I mean the large-scale drivers, in the sense that, say, there's SSTs, we have SSTs, and then we have snow is, snow also comes from, say, the Eurasian snow cover, for example, is coming from the precipitation scheme itself. And then there is, say, the soil moisture, which is again governed by a bunch of things. It is governed by how much water comes. Say, for example, the precipitation the rainfall that falls on the ground, as well as the, say, surface runoff, subsurface runoff, and then the fluxes, the latent heat and the sensible heat fluxes that the surface parameterization computes. So they decide the final soil moisture and its interaction with the atmosphere. So when I say, so first thing is when I say SST, we should, all these runs that we have done, this is mostly looking at the atmospheric component with prescribed SSTs. But when we start looking at coupled runs, we also have to make sure that our SSTs are correct. So SST is a driver of monsoon. That is what I meant. And then, so the drivers have to be correct. Say whether it is Indian Ocean SSTs, whether it is Pacific SSTs, whether it is Atlantic SSTs. So the SSTs have to be correct, or the if you want to say that the ocean heat content has to be correct in a way. If you look at a more slow variations,
right?
And then so these have to be correct, and their relationship, in the sense how they affect Indian summer monsoon. That relationship has to be correct. Once both are correct, then only we get the simulation correct. Otherwise, if one of them is wrong, we don't get the right answer. Even if we may get it for the wrong reason.
Yeah. So related question, Sandeep, you give the right SSTs, and yet it rains too much over the Western Indian Ocean.
Yeah. Because the atmospheric component has issues. When I say atmospheric component, it could also be the say, for example, whether it could be the fluxes that go into the atmosphere, whether the latent heat fluxes, the amount of moisture it gives to the atmosphere, and also even if that were to be correct, it's say the atmosphere gets the right amount of moisture because the SSTs are right. Still, then the convection scheme should know how to handle this right amount of moisture. If it doesn't know, then you get the precipitation incorrect.
All right. Mm-hmm. Yeah. Thank you, Sandeep.
Yeah.
So I have one question.
Yes.
You talked, of course, a lot about biases in different variables. What variables are actually modeled well?
The model did well.
Yes, I mean, is that list much longer? And
no. So not really. So these are some of the important features that we were looking at. And then so the model did well. For example, when we did, I might have it somewhere, but not in this presentation. So say we look at cloud, for example, we look at low cloud, medium cloud, high cloud, and then say the low clouds were significantly improved
I guess, so sorry, let me rephrase the question. Not necessarily improved in terms of what people had done earlier and what you're doing now. I'm just saying in general, in many of these models, which variables are represented well, not just as, so to say, averages over regions and so on, but right now, for example, for precipitation, say, you're looking at lots of details of whether you get the spatial patterns well represented, whether you get the onset, so the temporal aspects well, and the distribution, all three. Is that asking too much or not? That is, do we get temperature perfectly well represented in terms of patterns? Not the mean temperature over India, but the pattern of, if I were to plot the map of temperature. Observations. Is that so? What variables are actually represented well?
So
in that sense.
So, for example, temperature is a more homogeneous field and then less noisier than precipitation. So yeah, definitely temperature simulations, the pattern correlations are like 0.97, 0.98. So temperature is definitely better simulated than precipitation. Yes, and then the large scale circulation is also reasonably well simulated. So in general, we can say the larger scale features are well simulated and the finer scale features are not well simulated. So in terms of spatial scales,
But is there some kind of slight? And I think this is partly related to what you're saying at the end about the holistic approach. Is there a understanding of, so say, different types of not types, or different variables which are represented well and which are not represented well? Has it been done in a kind of exhaustive way? Let's say for some region, let's say Indian region or something, maybe not globally. I don't know.
I might have something to show. I don't know whether I have it here or not. So yeah, I mean, we look at a bunch of variables actually. I mean, in terms of Taylor diagrams, for example, and then we look at various, say, but then in the context that you are asking, I mean, people have done it, but then the kind of things that we look at is, say, for example, what is how well the, say, precipitation is, say, precipitation when we talk about total and then convective and a large scale, how well the, say, 2-meter air temperature is, how well is the, say, the low cloud is, the medium cloud is, the high cloud is, and then how good the OLR is. So all these things are there. I mean, we look at all these things. And then,
Okay.
Hi, Sandeep. Venu here.
Hi, Venu.
So you've been talking about seasonal mean, and I keep seeing with all model comparisons they do that. What is your take on actually looking at the average intensity? Meaning, when it rains, what's the intensity? Because let us say it rained a little longer. You're likely to get a wet bias and at the same intensity. So does that happen for the Indian region? So from your PDFs, it seems like a lot of the high intensities, what you were just saying, the fine scale features are not getting, not this one. So by the way, related question, how does IMD PDF look on this?
I don't know.
Was trim chosen for judicious reasons?
No. In principle, we should be looking at observational uncertainty, so we should do it. Actually, we have not looked at it. But then I remember doing IMD as well, and it's not that. I mean, not too different than this what we see.
Okay.
So I mean, coming back to your question, so we have not looked at what you are asking. I mean, so that would be a good diagnostic to look at, which you have looked at observations. I mean, how much it rains, when it rains. So we have not looked at, say, for example, we are looking at daily accumulation here. We are not really looking at densities. We are looking at daily accumulation. Daily accumulation can come from, say, low intensity rainfall for longer durations, or from high intensity rainfall for lower durations. So those kind of IDF curves we should look at high frequency, at high time temporal resolutions. I mean, sub daily and so on, maybe hourly or something.
Yeah. Okay. All right.
Any other questions? Okay, I guess if there are no other questions, then let's thank Sandeep again.
Thank
and
you.
we will continue the discussions later. Okay. Yeah. Thanks, everybody.
Thank you, Sandeep.
Thanks. Thank you.